Previously, we learned that when a rotor of a single-phase induction motor is rotating in the presence of an oscillating single-phase magnetic field, it produces a rotating magnetic field, in this case, in the counterclockwise direction. In order to analyze this from a different perspective, I'm going to use something called the double field revolving theory, which we will use to explain this dilemma of no torque at startup, yet torque once the rotor is moving in either direction. This theory is based on the fact that an alternating sinusoidal flux phi, which is equal to phi m sine omega t, can be represented by two revolving fluxes, the magnitude of each is equal to 1/2 of the maximum value of the original flux, phi m all over 2, and each rotating at synchronous speed in the opposite directions to each other. Consider these two rotating magnetic fluxes, phi 1 and phi 2, each of the magnitude of which is phi m all over 2, and rotating in opposite directions with angular velocity omega. Let the two fluxes start rotating from the x-axis at t equals 0. After a time t, the angle through which the flux vectors have rotated is omega t. Resolving the flux vectors along the x and y axes, we have the total x component is made up of plus phi m over 2 cos omega t and minus phi m all over 2 cos omega t, which sums to 0. The total y component is made up of plus phi m all over 2 sine omega t plus another phi m over 2 sine omega t, which sums to phi m sine omega t. Remember, we have only calculated the x and y component. The resultant is found using the Pythagorean theorem, which is equal to the square root of the y component squared plus the x component squared. The instantaneous value of flux due to the stator current of the single-phase induction motor is given by phi is equal to phi m sine omega t. Watch this action in relatively slow motion. We have a magenta phasor on the right rotating clockwise, and we have an orange phasor on the left rotating counterclockwise. The resultant, when added together, is shown blue along the y-axis. I have recolored the vectors in order that we can follow the action better. The magnitudes of the magenta and the orange vectors are 1/2 phi m. So you get plus 1/2 phi m, then minus 1/2 phi m along the x-axis, which sums to 0. And you get plus 1/2 phi m and plus another 1/2 phi m along the y-axis, which sums to the blue resultant, which goes plus or minus phi m along the y-axis. As the orange and magenta phasors continue to rotate, the resultant will shrink to 0, then expand plus phi m along the y-axis. So you could actually see this theory working as the two phasors, orange and magenta, rotate one clockwise, the other counterclockwise. The resultant will be a pulsating stationary phasor that does not rotate but pulsates, in this case up and down from minus phi m to 0, then up to plus phi m and back down again. Consider the case that the rotor is stationary and the stator winding is connected to a single-phase supply. The alternating flux produced by the stator winding can be presented as the sum of two rotating fluxes, phi 1 and phi 2, each equal to 1/2 the maximum value of the alternating flux, and each rotating at synchronous speed in opposite directions. Flux phi 1 rotates in a counterclockwise direction, and flux phi 2 in a clockwise direction. The flux phi 1 will result in the production of a torque T1 in a counterclockwise direction, and flux 2 will result in the production of a torque T2 in the clockwise direction. At standstill, these two torques are equal and opposite, and the net torque developed is zero. Therefore, a single-phase induction motor will not be self-starting. This fact is illustrated in the torque slip chart here for a rotating field on an induction motor. Remember now that the slip is ns minus n all over ns times 100%. The torque due to phi 1 is shown here in magenta and tends to drive the rotor in a clockwise direction. The torque due to phi 2 is shown here in orange and tends to drive the rotor in a counterclockwise direction. A slip of greater than 100%, is the rotor turning in the opposite direction to the synchronous direction. At standstill, these two torques are equal and opposite, and the net developed is zero. Therefore, a single-phase induction motor is not self-starting. So if we added the two rotating vectors together, we are essentially combining the torque slip curve together, which would look like this. If it were at standstill and we applied a sinusoidal current to the single-phase motor, the rotor would not start. Essentially, it would vibrate, as the torque slip curve indicates. However, if we gave the rotor a push in the clockwise direction, reducing the slip in that direction, you can see that there will be a torque develop that will continue to push the rotor in the direction in which it was started. As that happens, torque increases and finally gets to a steady state value where no torque is being applied and the rotor will continue to rotate. Keep in mind, though, that if there was a load on the rotor, it would settle out somewhere above zero, but we're assuming there is no load on this rotor. Now, if we decided to push the rotor in the other direction, a similar thing would happen, only in the counterclockwise direction, as we rotate in the counterclockwise direction. The torque will increase in a negative or counterclockwise direction, and the speed will increase until it reaches close to the synchronous speed in that direction. Now that we understand the double revolving field idea, let's translate it into an equivalent circuit. The alternating stator field can be modeled as two rotating fields, one forward rotating field and one backward rotating field. Each field acts like its own small induction motor. Therefore, we represent the single-phase motor as two parallel circuits, one for the forward and one for the backward field. Each of these fields interacts with the rotor to induce currents, just like in a three-phase induction motor. The forward field sees a slip S. The backward field sees a slip 2 minus S, because it's moving in the opposite direction relative to the rotor. Each field induces its own rotor current and produces its own torque. The forward field produces a useful torque, the one we want. The backward field produces opposing torque, which subtracts from the forward torque. At standstill, S equal to 1, Both fields produce equal and opposite torques. The net torque is zero. That's why the motor doesn't start by itself. Each branch has half of the stator resistance, Rs divided by 2. Each branch has half the stator leakage reactance, JXL all over 2, and each branch has half of the magnetizing reactance, JX all over 2. The rotor circuit, referred to the stator, has R'(S) all over 2S for the forward field, and the rotor circuit, referred to the stator, has R'(S) all over 2 times the quantity 2 minus S for the backward field. Then the total current drawn by the motor is the sum of the currents in the forward and backward branches. This split equivalent circuit makes it possible to calculate torque, current, and power separately for each field, and it makes it possible to show why the net starting torque is 0, since S equals 1, forward and backward torques cancel each other. And finally, it makes it possible to show how the net running torque develops when the rotor begins to move. The forward torque becomes dominant because the slip gets smaller, and the backward torque weakens because the slip 2 minus S gets large. Ready to go beyond just solving problems? If you've been following my daily post and enjoying the sample problems, you're going to love this. All of these problem sets and more are now available, or soon will be, on my official course site, my stand store for electrical training. Just go to the web address that you see at the bottom of this slide, https://stand.store/GVB.